Hello, here's the Physics 2211 Lab 4 and oscillations for Georgia Tech. Today we'll be starting with the table of contents, introduction, fundamental principles, experimental design, computational model results, and what does it mean at the end. For the introduction, the purpose of this lab is to use the fundamental principles to predict the motion of a system consisting of a spring and mass, and, and to demonstrate these principles through experimentation. Our system includes mass, spring, and earth with no external surroundings, contributing energy based on the energy principle. We'll be applying Newton's second law and the energy principle, recognizing that the spring force acting on the mass is proportional to the spring's displacement. According to the energy principle, the total energy of the system remains constant, composed of kinetic, gravitational, potential, and spring potential energy, which oscillate all together to maintain the net zero energy. Next, we're going to be going the equations we need. We're going to need the kinetic energy, obviously, gravitational potential, spring energy, total energy, force due to gravity, velocity update, position update, the period of oscillation. And spring constant. This is for the what if question at the end. So we'll get more on that later. Next is the experimental design. So our initial conditions are going to be time equals 0 seconds, velocity initial is 0 meters per second. The initial position is about 0, 0, 0. Force of gravity is obviously going to be negative 9.8 meters per second in the y direction. The mass is 0.7 grams. K constant was defined as 6.83, and LO was 0.4 meters. So for the computational model, um, the we incorporated the initial conditions and equations for the kinetic energy, gravitational potential, and spring potential, allowing us to see that the total energy remains constant, confirming the energy principle. Within the while loop, we calculated the net force, applied Newton's second law, velocity and position update, and updated the spring force accordingly. Then we computed the energy changes and compared the total energy at each step to the initial energy. Our results showed that the experiment's x and y positions closely match the computational model, as indicated by the overlapping position of graphs you'll see in a second. Additionally, while analyzing the changes over time and energy, we can observe that the energy remains constant while kinetic, gravitational potential, and spring potential energies all oscillate just as expected. Kinetic energy oscillated at twice the rate of the potential energy changes demonstrated in the energy principle. So here's our results. As you can see, um, the experiment x and y positions closely match the computational model. Not quite, they do overlap a little bit. But we also see that as the energy changes over time, the total energy remains constant, and the gravitational potential and spring potential energies oscillate. And as I said earlier, you can see that the kinetic energy oscillates at twice the rate of the gravitational potential and spring potentials. So some errors in this are selecting the center of mass. So and also some air resistance. So we can confirm that the energy principle is satisfied, but there are some misalignments here, as you can see. The peaks don't quite line up together. I'll go over that more in a second. So what does it mean? The first question. Um, is the energy principle satisfied? Yes, it is. So basically, this is asking if the total energy is zero, and it equals the kinetic plus the spring potential plus gravitational potential. And it does, as you can see here, delta E. This remains at zero the entire time, and everything oscillates around it, and they all add to zero. So you can see this bulge here and this bulge here added up will equal this little bulge here. So it works really well. Next, what does it mean? Part two. Basically, this is just asking to compare the two periods. And as you can see, the periods are a little bit different. So we have 1.6 seconds for the first period, and the computational is 1.54 seconds. And here's our equations from earlier, and this is what I used to calculate the t. And so the importance of this is that the different t's can lead to error. The peaks don't quite line up like you'd expect them to, as I addressed earlier. There is a little bit of mismatch and overlap here, so that would cause some error. Anyways, the conclusion for this is the experiment is in agreement with Newton's second law, the energy principle, and the experimental model and computational model both agree. So yeah, hope you enjoyed the video. Thank you.